You hear that? Isn't that relaxing? Sometimes when I'm here in the classroom, there's no kids in here like I'm used to. And so sometimes I'll just have some nice music on while I'm working and enjoy that. It keeps me relaxed and keeps me working hard. Sometimes music helps us, doesn't it, work? Well, that's a question we're asking today. What is sound? How do we have music? What makes the beautiful sounds that we like to hear? What makes those sounds that we enjoy when we listen to music? And so this first lesson of Unit 4, which we're beginning today, our essential question is that. What is sound? How do we hear that? How does this little phone make a noise that we can hear? And where did that noise come from? And how did it get inside the phone? And, well, we're going to answer some of those questions today. What is sound? We're on page 149 of your science book. So if you would turn there, I want you to follow along with me as we go through this lesson together. What is sound? Waves of sound. You may have seen water waves. You've seen waves at the beach, right? Waves that look like this. Water waves move in an up and down motion and as shown here. No matter how a wave is shaped, it carries energy. So we just took our test yesterday on energy. And we see waves move up and down. If you're in there, you kind of go up and down, don't you? The waves lift you up and bring you down, up and down. If you go to splash country and you get in a wave pool, you'll float up and down, won't you? The waves coming in. And they carry energy. They can move you. They push you. Sometimes if you get in a rip current in the ocean, it can pull you out towards the ocean. That's a bit scary. Well, just like there's waves in the water, there are waves of sound. Sound travels in waves, not waves that we can see, but with our eyes, but they travel in waves. Some waves are long and flat. Others are tight and tall, but all waves move from place to place in a regular way. Musical vibrations. What you were listening to is what started the video was guitar music, just nice guitar playing. And those strings, when you pluck the string of a guitar, it vibrates, moving the air and causes sounds to move. Water waves carry energy as they move, one after another across a lake. A wave, here's a highlighted word. You want to underline this in your book. It'll be one of your definitions for today's assignments. You should be getting good at this now. A wave is a disturbance that transmits energy. You need to underline that so you can go back and find the answer in a few minutes. A wave is a disturbance that transmits energy. There are other kinds of waves that you can't see. Sound is a series of vibrations traveling in waves. There's another word. Vibrations are the back and forth. Let me highlight. Come on. Vibrations are the back and forth movements of an object. Vibrations are the back and forth movement of an object. When you pluck a guitar string, the string vibrates, causing sound waves. The vibrating body of the guitar makes the sound louder. So if you have a guitar, or maybe there's a guitar in your house and your parents don't mind you using it, try it sometime. When you pluck that string, you can watch it vibrate, and that's what's making the sound. It's making sound waves through vibration. Thinking of a spring toy can help you understand compression waves. You ever played with a slinky? The coils in one area become bunched up. Okay, you see that? Or compressed. Then they stretch out or separate. These compressions and separations occur along the length of the spring as the wave moves away from its starting point. Let's read down here about those compression waves. Musical instruments aren't the only things that make sound. Striking the head of a nail with a hammer causes sound vibrations too. You clap your hands and make a sound. Yep, that was a sound. You made vibrations. Many animals make sounds by moving a column of air up through the throat and mouth. I'm doing that right now. I'm an animal making a sound, making air come through my throat and mouth. Your vocal cords vibrate in your throat. All sound vibrations travel in compression waves. As a compression wave moves, molecules of air or other matter are pushed together or compressed, like we saw up here. Then the molecules spread apart. Sound energy moves away from its source as this bunching and spreading of molecules is repeated over and over. So if you got a slinky, you know what a slinky is, right? And you set it at the top of the stairs and you let it start going down, it would compress and then it would bounce and lift back up and go to the next stair, compress, come back up, go to the next stair. That's how sound travels. It moves like that, compress, kind of like a spring moving like that. Is what they want you to see here. Sound energy moves away from its source as this bunching and spreading of molecules is repeated over and over. Your ears detect sound waves when the waves make parts of your ears vibrate. Your brain interprets these vibrations as sound. That goes right along with our reading unit. We looked at sight last week, and sound works by that part of our ears vibrating down there, our eardrum, that little flap of skin and our membrane in our ear. It catches those vibrations and sends the sound to our mind, to our brain rather. And we can tell what that sound is most of the time. What does it sound like? A bird's song has a high pitch and a high frequency. Those are two words we're going to look at on this page, pitch and frequency. Its sound waves have many vibrations per second. This dog's bark has fewer vibrations per second. It has a low pitch and a low frequency. So as we look down here at the bottom of the page, we'll come back up to these pictures and talk about what pitch and frequency are. Our world is full of sounds, many of them pleasant, others are harsh or annoying. People measure characteristics of sound in order to understand, describe, and control how sounds affect our ears. Pitch and volume are two useful ways to measure sound. The highness or lowness of a sound is its pitch. Underline that in your book. How high or how low a sound is its pitch. If you were in music class, Mr. Meal would say, sing on pitch, because he wants you to sing at a certain pitch, a certain highness or lowness, so you're on the right note that everybody else is singing. It's how high or low a sound is. A flute produces high-pitched sounds. A tuba produces low-pitched sounds. Frequency is the number of sound vibrations that occur during a unit of time. A sound with a high pitch has a high frequency. Oh, we didn't do this, did we? We need to highlight this. Frequency is the number, highlight or underline this. Frequency is, okay, come on. Frequency is the number of sound vibrations that occur during a unit of time. A sound with a high pitch has a high frequency. Low pitch sounds have low frequency. So let's look up here back at these illustrations again. So a little bird, it's going cheep, cheep, cheep. It's high frequency. Look how many waves there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See how many waves there are? There's a lot more tops of the waves here. There's 1, 2, 3, 4, 5. It's a high frequency. If both of these animals, let's say, were barking for 5 seconds, that would be 5 frequencies in 5 seconds. The dog only has 1, 2, 3. So the waves of the dog's bark are less frequent because it's a high pitch. It has a high number of frequencies. Lower pitch has a lower number of frequencies. And then, of course, you know this. You need to underline this. Here's another vocabulary word. The loudness of a sound is its volume. You have a volume control. I can turn mine up on my computer, or I can turn it down. That's how loud the sound is going to be. And volume is measured in units called decibels. Decibels, abbreviated dB. The softest sounds that humans can hear are near 0 decibels. The humming of a refrigerator is 40 decibels. Heavy traffic in a city is about 85 decibels. Any noise at this level can cause hearing loss if a person listens for a long period of time. It's wise to wear earplugs if you'll be exposed to 15 minutes or more of noise at 100 decibels. No more than 1 minute of noise at 110 decibels is safe without ear protection. Your mom ever said, turn those headphones down, I can hear them all the way over here. Well, she's trying to save your ears because listening to sounds that are too loud for a very long time can damage your hearing and cause you not to be able to hear anymore. So listen to your mama. Next page. Okay, so we're looking at some things here. Did it show it on this page? You can't really see it there. So lightning here. If you're close to a lightning strike, the resulting thunder can be loud enough to cause pain. It could be 120 decibels. Sounds that are 85 decibels or louder can damage your ears. It's like somebody using a jackhammer. A big train going by, 80 decibels. Okay, turn that down. The number of sounds in the first column, 1 through 6, number the sounds in order from quietest to loudest. Put a star next to any sound that could damage your ears. Okay, so let's see. Here's the sound source. Here's the decibel level. So it wants to put them in order from quietest to loudest. So we're looking for the smallest number. Whispering voices like this little girl would be the quietest. Number 1. What would be second? How about normal conversation is just 60 decibels, just like we're having right now. Next would be a power lawnmower. I don't know. My lawnmower sounds pretty loud when I'm sitting on it sometimes. That would be third. And then fourth would be 105 decibels. Personal stereo system at a highest volume. Wow. The next one would be the ambulance siren, number 5. And the loudest would be a firecracker, number 6. So which ones could damage our ears? Sounds that are 85 decibel or louder can damage your ears. So the firecracker, the ambulance siren, the lawnmower, and a top volume stereo system could all damage your ears. So be careful if you're using any of those. Look at waves. A tiny kitten and an adult lion make very different sounds. What words would you use to describe exactly how they are different? Well, the tiny kitten, he has a high pitch, doesn't he? Meow, meow. And a lion, roar, low roar. People don't only use words to describe sound, they use diagrams. Waves consist of curving lines that go up and down as they move away from the sound source. Each high point of a wave is called a crest. So the top of these waves right here, they're called crests, the very top of a wave. Each low point is called a trough. So the low point of the wave is called a trough. The distance from one crest to the next crest is called wavelength. So the top of this right here to the top of the next wave, that is called wavelength. Wavelengths can be found by measuring between troughs too. It would be the same if you measured from the bottom of this trough to the bottom of this trough. It would be the same as measuring from crest to crest. Turning on a jet engine produces very loud sound with large amplitude. I bet we're going to find out what amplitude is next. Okay, so wavelength, top of one crest to the top of the next. Here we see those compression waves again. The taller the wave is from its resting point. Okay, so think of about the middle of a line, the wave. The taller it is from its resting point, the larger the amplitude and the more energy the wave carries. So think about the top of the ocean, okay, being that yellow line going across there. How high the wave is, not the distance between, that's wavelength, but how high the wave is the amplitude. And the higher it is, the more power, more energy it carries. That makes sense, doesn't it? If you're standing out here in the ocean and a big, huge wave crashes down on you, you're going to feel all that energy, aren't you? Dropping a pin onto a hard surface produces a soft sound with small amplitude. Those waves are not very high at all, are they? So the quieter the sound, the lower the amplitude, the lower the energy. The size of the vibrations of a sound wave is its amplitude. You need to underline that. You know, it's going to be a vocabulary word. The size of the vibrations of a sound wave is its amplitude. And these are these represents the vibrations, the up and down, up and down. How high it is and how low it is represents the amplitude. If it's high here, it's going to be low here. So just think of it as how high the wave is above its resting point, which would be like the top of the ocean And the higher wave has more amplitude, more energy. Amplitude describes the amount of energy in a wave. A jet engine produces a sound wave with an extremely large amplitude. On the other hand, a pin hitting the floor produces a sound wave with a very small amplitude. As you may have guessed, the volume of a sound and the amplitude of a sound of its wave are related. Loud sounds have large amplitudes, whereas soft sounds have small amplitudes. Amplitude is measured by finding the distance from the wave's highest or lowest point to its midline. The midline is a horizontal line drawn straight across the middle of the wave. The midline is what we've called here, like we said, the top of the ocean, how higher the wave is. This yellow line going across is the midline of the wave. Okay? So how high the wave is its amplitude, the distance from the top of one crest to the other crest, or one trough to the other trough, is its wavelength. High volume means high amplitude. Lots to remember today, isn't there? The travels of sound. Sound can travel through walls, windows, and floors, as well as air and water. Does sound travel at the same speed through solids, gases, and liquids? I'm sitting at my desk right now talking to you, but in this ear I hear over there, I hear Miss Williams talking through the wall. She's teaching her class something about science right now too. So sound traveled all the way through the wall into my room from her room. So sound can travel. How does it do that? The sound of this boy's voice moves through the gases in the air and the liquid water before reaching the other boy's ears underwater. Okay. Have you ever tried to talk to anybody underwater? It's kind of fun, isn't it? You can hear them. It's kind of muffled, but you can hear them. Sound travels in waves, but sound can only travel if there are particles that the waves can cause to vibrate. Most of the sounds you hear move through the air. Air and other gases have particles that vibrate as the sound energy hits them. Liquids and solids are also made of particles, so sound waves can move through these materials too. However, if there are no particles to move, then sound cannot travel. What would happen if an astronaut dropped a heavy rock on the moon? Is there any air on the moon? No. So you would not hear it hit the ground because there would be nothing for sound waves to travel through because there's no air on the moon. Would it fall with a thump? Nope. Since the moon does not have an atmosphere, there would be nothing for the sound waves to travel through. So dropping a rock would produce no sound. You know that old silly question, if a tree falls in the forest and nobody's there to hear it, did it still make a sound? What do you think? Of course it did. It just made a sound, just nobody heard it because there's still air there, so it made a sound. Let's go to the next page here. Oh, we got to do the math. Do the math. All right, sorry about that. I had another teacher asking me an important question about RTI, and I needed to answer him right away. Let's go back to page 157 here. Do the math, multiply whole numbers. You know, we're probably not going to do this math. We've not worked on multiplying yet, have we? But we're going to read this down here. Sound waves travel through different kinds of matter at different rates. The speed at which sound waves pass through solids, liquids, and gases has to do with how their particles are arranged. Particles in a solid are packed closely together. The particles in gases are far apart. Liquids are in between. For this reason, sound travels through gases more slowly than it travels through liquids and solids. That just makes sense, doesn't it? Think about the particles. Everything's made up of particles and atoms. And so if you move your hand through the air, just move your hand. It moves pretty easily, doesn't it? Now move it through whatever you're sitting on, your bed or your desk. Ow. It didn't move. My hand didn't move through it at all because the particles are packed close together. They're so close together you can't move. My hand can't move through them. And water, you know what it feels like in the bath or in the pool to try to move. You can't move as quickly as you can through air, but it's not that hard. Well, the harder something is, if it's solid, the faster sound can move through it because remember, it bounces. It needs those particles to move. And since there's more particles in a solid object, the sound can move faster through a solid object. So sound actually moves faster through water than it does air. It doesn't travel, it doesn't make it as clear, does it? But it still moves faster because water has particles that are closer together than air does. When you knock on the door, the sound moves through a solid, like wood, and through a gas, air, on the other side of the door. So we'll go back to this chart. We're not going to try to find exactly, but how long would it take a sound to travel 4,575 meters through each type of matter? Well, let's just say this. Cast iron, like a skillet your mom might cook in, the speed of sound would be 4,575 meters per second. Well, it would take it 1 second then, right, to move through, to travel that far. This moves, dry air is 300 meters per second. So we'd have to figure out how many times 300 would go into 4,575. It'd be about 150 something. So 150 seconds to go through dry air to get that far. Pure water, something like 3 seconds. So the point of this is sound travels through solids like iron much faster than it would through air or water. The more particles there are, the quicker the sound travels. Sounds in the air. Today's smartphones, also known as cell phones, are like mini computers. You can use your cell phone to access the internet, to send emails, to listen to music, to watch videos, to store content, and to take notes. When you use your cell phone to talk, you use radio waves. A cell phone converts your voice, your voice is made of sound waves, into radio waves. These waves then get sent to a cell tower. From here, the waves are relayed to other cell towers. Finally, the tower sends radio waves to a receiving phone. This entire process happens almost instantly. That's amazing, isn't it? It's pretty amazing that I'm sitting here right now. The computer is recording my voice. And when you click play, instantly you could hear my voice. It's pretty amazing how technology works. So when I call somebody on my phone and I type in a number and I call and I say, hello, think about that. It's pretty amazing. They might be in Canada. They might be 1,000 miles away, but I could say hello, and they heard my voice as soon as I said it. Think about how fast those waves travel. And it turns our sound waves that go into the phone, and it turns them into radio waves to the cell tower, to another cell tower, to another cell tower, till it gets all the way to Canada. And then they hear it's coming out of their phone as another sound wave. And it happens instantly. It just amazes me that it works like that. Doesn't it you? How cell phones help us communicate. When you talk on a cell phone, the sound waves of your voice are converted into digital code. The code is then sent as radio waves through the air. The sender's radio waves reach cell phone towers, which exist in a network around the world. The waves are sent from tower to satellites in outer space, and then to other towers. So when you talk on your phone, your voice travels to outer space, to a satellite, to another tower. That's crazy. The radio waves are received by the destination cell phone, which converts them back into sound. Wow, isn't that cool? Let's see if we can figure this out. Cell phones convert sound waves into radio waves. They are then sent to a cell tower. From here, they are relayed by other towers. They eventually arrive at a blank near another phone. I guess it's another tower near another phone. Okay, so pretty interesting. It's amazing to think about how they work. Well, here's a sum it up page. You've got your answers at the bottom of page 160 in your book. Go ahead and fill those in to review the lesson when we get done with the video. And this will be today's assignment. You're going to have 6 words. You can do them in your book before you go do the assignment. It'll say Unit 4, Lesson 1, Vocabulary. This will be your assignment today. But if you match these words to their definitions right now, don't worry about the picture. Just match the word to the definition. Then you'll be able to use your book to help you answer the vocabulary questions for today and make an easy peasy 100. Define wave and then explain how vibrations, waves, and energy are related to sound. Well, a wave, let's see if we could find it over here. What's a wave? It's a disturbance of particles in matter as a sound. No, that's not it. A disturbance that carries energy. That's it. A wave is a disturbance that carries energy. How are vibrations, waves, and energy related to sound? Well, a wave is a vibration. So when we speak, we send out a sound wave that's a vibration. And the higher the crest, the more amplitude, the more volume, the more energy the wave and the sound has. There we go. We used all three of those words. Label the pictures 1, 2, and 3 to indicate the speed at which sound travels through each kind of matter. Let 1 be the fastest and 3 be the slowest. Well, we know that the fastest thing would be a solid. So what's solid here? This door is solid, so that would be the fastest. Now, I don't like these because there's solids on the outside of both of these. But they're saying inside a balloon would be air, inside a cup would be liquid. So we know the next thing that would be traveled the fastest through would be the liquid. So that would be number 2. And the slowest thing that sound waves travel through is air. So that would be number 3. Okay? All right, now we're looking at these, and we're going to decide if the volume and pitch is high or low. A fire engine siren, it's definitely got high volume, and its pitch, it's high, isn't it? A bird chirping, some mornings they wake me up, they're so loud. Sometimes they're just kind of soft, but I'm going to say high volume. And the pitch is high of a bird chirping. A large diesel truck engine, it's got high volume, but it's got a low pitch, doesn't it? Refrigerator hum, can you hear your refrigerator right now? It's got a low volume, it's pretty soft, and a low pitch. Falling rain, I like falling rain. It's relaxing too, isn't it? It's got kind of a low pitch and a low volume and low pitch. Thunder, it's got a high volume and a low pitch. How are pitch and frequency related? Well, remember, the higher the pitch, the higher the frequency. Remember those waves, the little bird, the wave beside the little bird? There was 5 waves per second or whatever it was, and the dog only had 3. It's because the higher the sound's pitch is, the higher the frequency, the more waves there are. How are volume and decibels related? Well, we read that we measure how loud volume is. We measure volume in something called decibels. The louder the volume, the higher the decibels. Okay, write a caption for each picture using the term amplitude. Well, let's just compare and contrast. Which one has the higher amplitude? Obviously this one. Remember, amplitude is how high the waves are. So this picture has a high amplitude, and this picture has a low amplitude. Okay, draw a sound wave that has at least 3 crests and 3 troughs. Draw an arrow above that shows the direction the energy is traveling. Well, I can't really draw on this page, but you could draw it right there in your book if you want to. Draw some waves, kind of like this. You could draw an arrow to show which way it's traveling. Below, draw dots to show the 2 areas where air molecules are crowded. If you had a compression waves, you could have some waves that are close together, and 2 areas where they're spread apart. Okay, so these, when they're closer together, they're compressed. But if they were spread out, these are all equal. But compression waves, remember, let's go back to that page so you know what it's talking about. See, these waves are more spread out and these are more close together. That's what it's talking about. Those ones that are bunched together are compressed. They're compression waves. Okay. And we're going to move on down here. Let's label the wave. Use C for crest, T for trough, W for an area where you could measure wavelength, and 2 A's where you could measure amplitude. So the crest, we could draw a C right here if you want to in your book. The top of the wave is called the crest. We could put a T down here for trough. It's the bottom of the wave. A W for where you can measure wavelength. Well, remember it's from one crest to another or one trough to another. You put W between there or up here to show that that's how you measure wavelength. Amplitude is how high the wave is. You could draw an arrow from the line to the top of the wave. That would be its amplitude, or the line to the bottom. That would be its amplitude as well. 4 sounds that could damage your ears. Well, what have we heard? Fireworks, sirens, loud music, and what else? A jet plane. There we go. How could you protect your ears? You could use earplugs. All right. And that's all of today's lesson. So I hope you've learned a lot about how sound travels today. Thank you for listening. Now I want you to go and do your assignment. It'll be these vocabulary words right here, these 6 words. Make sure you do page 161 and make sure you got them right. You can go back and look. We underlined these in the text today so you can get an easy 100 for today's assignment. All right, go do that now. I'll see you later.